Hello class, so welcome again to CHM 322 class. Today we shall proceed from where we stopped in the last class. Last class I told you we have the dextrorotatory and the levo rotatory forms of glucose, and we decide this based on the direction or the position of the hydroxyl group. If you go back through the last video, you see the last thing I was talking about was that we identify dextrorotatory and levo rotatory based on the position of hydroxyl group. If it's on the right, we call it the dextrorotatory. If it's on the left, we call it the levo rotatory. But I told you this method is not good enough for us to identify these molecules properly. So we came up with a better way, and that was what I said we're going to begin to consider today. So today we'll be looking at what we call the sequence rule for specification of configuration. The sequence rule for specification of configuration. Now, a general method applies to the configuration at each chirality center instead of to the whole molecule. In the case of the levo and dextrorotatory we talked about, the whole molecule is considered. Once we see the hydroxyl group on the right, we say it is dextrorotatory. Once we see it on the left, we say it is levo rotatory. But in this case, we do not give a configuration to the whole molecule, but instead the general method applied to the configuration at each chirality center. So in this case, we are going to be identifying each chirality center and naming it according to the chirality center. Also, the configuration is specified by the relative positions of all the groups with respect to each other at the chirality center. So we are going to consider the substituents attached to the chirality centers, and we are going to name it relative to those substituents. You shall understand what this means in a moment. The groups are ranked in an established priority sequence and compared. So each group that are around the chirality center, we rank them using established priority sequence, and we compare them to each other, and that's what will tell us what type of rotation is occurring there. The relationship of the group in the priority order in space determines the label applied to the configuration according to a rule known as the Kahn-Ingold-Prelog rules. So the Kahn-Ingold-Prelog rules is the one we are going to be applying to tell what will be the configuration in each chirality center. So rule number 1, look at the 4 atoms directly attached to the chirality center and rank them according to atomic number. So we are going to look at the 4 atoms that are directly attached to the chirality center, and then we rank them according to atomic number. So atom with the highest atomic number has the highest ranking, and atom with the lowest atomic number has the lowest ranking. Very, very important. We rank them based on atomic number. That's number 1. Now, if we look at this again, from here now, for instance, we can see I have bromine, chlorine, sulfur, phosphorus, oxygen, nitrogen, carbon, and then these isotopes of hydrogen. Now, bromine will be the highest rank in this group. Bromine will have the highest rank in this group. And why is bromine having the highest rank? It's because the atomic number of bromine is 35. You can see it will be ranked higher than chlorine, which is 17, to be ranked higher than sulfur, which is 16, to be ranked higher than phosphorus, which is 15, and so on, up to hydrogen, which is 1. So we put the highest ranking to the atom that has the highest atomic number. So your understanding of atomic number will have to play out here, but not necessarily. Sometimes you might not even know the exact atomic number of the atom attached. For instance, if I attach iodine, you might not know the atomic number of iodine, but you should be able to know that iodine will have a higher atomic number than chlorine, because both of them belong to the halogen group, that is group 7, and chlorine comes before iodine. Iodine is below bromine. So because of this, you can easily tell that iodine will have a higher atomic number. Nobody wants to know the atomic number. What we just want to know is which one will come first. So once you have the idea of the periodic table, most of the substituents you'll be seeing, they are substituents, they are atoms that you are familiar with, atoms like chlorine, bromine, carbon, oxygen, nitrogen. So you are expected to know their atomic numbers and know which one would appear first. So rule number 2, if a decision cannot be reached by ranking the first atom in the substituent, we look at the second, the third, or the fourth atoms until the difference is found. What does this mean? Let's see. Let's assume these are the two substituents that we have attached to our chiral center. Now, don't forget, these two substituents we are showing here, when the chiral center, let's say these are chiral center, which is a carbon, is on that chiral center, which is a carbon. You can see this sign here is to show that we tore these parts out of a particular molecule. So these parts are attached to a particular molecule. We don't know that. We are not concerned with that now. Our concern is if we have these two substituents on the same chiral center. This is the same chiral center, which is this carbon here. Which one will be given a higher priority? So how do I prioritize? We said if we cannot reach a decision, we cannot rank them based on the first substituent. We look at the what? The second. If the second can still not rank, we look at the third and so on. So let's see how that happens here. This is the atom directly attached to the chiral center. The chiral center here is carbon. In this case, I'm using this as my chiral center just for the purpose of this explanation. So now this is carbon that is directly attached to it. Carbon has the atomic number of 6. This is another substituent attached to the same chiral center. I want to also rank this one. And I say, okay, the atomic number is also 6. Both of them have the same atomic number. So which one will come first? I don't know. So what do I do is to move to the next substituent attached to that one. You can see to this carbon now, what is attached is hydrogen, hydrogen, hydrogen. So it doesn't matter which direction I go, it's still hydrogen. So I just let's stick to this one. It doesn't matter, you can pick anyone as long as it is directly attached to that substituent. But since they are all hydrogen, let's pick this. The hydrogen here is what? 1. Here, what is directly attached? Now, I don't pick this hydrogen because it has a lower atomic number compared to the carbon that is also directly attached. So it's the one with the highest atomic number I'm going to consider. So this is another carbon directly attached to this, which also has atomic number of 6. Now let's compare this 6 to 1. Which one will have a higher priority? This, because it has 6 and this has 1. So because the first one could not help us to determine which one will have the higher ranking, we went on to the next substituent. So that is how to approach it. If you look at the case of this, we have oxygen directly attached to our chiral center, and oxygen is 8 in the periodic table. Oxygen is 8 in the periodic table. This is also oxygen. So we've run into a problem because both of them are oxygen and they have the same atomic number. So we'll move to the next. The next one here is hydrogen, which is 1. Next one here is carbon, which is 6. So again, this is going to be the higher priority. If we look at this now, for instance, this is our chirality center. This is attached to a carbon, which is 6. This is also attached to a carbon, which is 6. Now, interestingly, if we move on to the next one, we can decide to move up or move here. You know, I've told you, we just move on to the atom that is directly attached to that previous one. But we always choose the one with the high. We can't choose hydrogen because they are carbons. If there's anyone with the higher atomic number, it is the one you have to consider. So carbon is here, so I pick carbon again, 6. This one still has carbon again. So it means we are still having a tie. We have to move on to the next atom until we can give a priority. So let's move to the next one, which is another carbon. This is 6. The next one here, there's no other carbon. The next thing we can see is the hydrogen. Either way I go is the hydrogen. If I go forward here, I see hydrogen. So I just pick this. This is 1. So this has it because this is 6 and this is 1. So this has the higher priority. And the same thing applies to that last one. So that is how to approach such situation. Whenever you see that you cannot determine by the first rule, they have the same atomic number, you move on to the next substituent. Rule number 3, multiple bonded atoms are equivalent to the same number of single bonded atoms. What does this mean? It means even if I have multiple bonds, the atoms are still equivalent to the same number of single bonded atoms. So for instance, this is this carbon is bonded to hydrogen and oxygen. You can see it is doubly bonded to oxygen, doubly bonded to oxygen. So this oxygen is bonded to 2 carbon. You can see because of the double bond. So it's doubly bonded, it's bonded to this carbon once, bonded to the same carbon again. So we say it is carbon-carbon. We said this is equivalent to, we have this carbon bonded to 1 oxygen, a different oxygen again, that's 2 oxygen. And then this oxygen is also bonded to 1 carbon, 1 carbon. So multiple bonded atoms are equivalent to the same number of single bonded atoms. The implication of this is that if I have a case of a double bond and I have another carbon that is single bond, the double bond will have a higher priority because the double bond is attached to 2 different oxygen. After I have considered this oxygen, I have to consider it again because this double bond is telling us that it's bonded to 2 carbon, not literally, but for the sake of this configuration, we take it as bonding double bond to mean that it is bonded to 2 carbons, just as though it is singly bonded to 2 different carbons. So in this kind of case, whenever you experience cases where we have double bonds, you must consider that double bond as being bonded to 2 different oxygen. If it's on carbon, it's being bonded to 2 different oxygen. So if you want to give a priority to one that is having 2 oxygen and one that is bonded to just 1 oxygen, we are going to give priority to the one with 2 oxygen. But in the case of this one, you can see this one is also connected to 2 different oxygen, which is equivalent to being double bonded to just 1 oxygen. So assign each group priority according to the Kahn-Ingold-Prolog scheme, with the lowest priority group pointing away. Look at the remaining 3 groups in a plane. The meaning of this is that the one that is the lowest priority group, you must put it on the point, you must make sure it is turning away, that is, it is not on a plane. We shall see what that means very soon. Clockwise is designated if the movement, after we have put the lowest priority on the part that will be moving away, that is moving towards inside, your paper, your plane, the paper, the images you'll be seeing here, they look plain because they are just on your paper. Like if you write those images on your paper, they just look plain, but in the real sense, images are not plain. Images are in 3 dimensions. Is that okay? So some images are actually moving away from you and some are moving towards you. Now, the lowest priority atom must be moving away from you. So in case of where that is not happening, there's something we do. So just have that in mind so that by the time I mention that, you'll be able to understand why it is so. Now, whenever we now have a clockwise situation, that means after we have prioritized and we are moving from higher priority to the lowest priority, if it is a clockwise direction, we represent it with R. And it is from Latin for right. This R is from Latin for right, but we call it rectus. So that's the Latin word and it means right. And then counterclockwise, if it's not moving clockwise, it's moving counterclockwise, which we also call anti-clockwise, we designate it as S. This Latin for left. This S is sinister and it means left. Is that okay? So now look at what we are talking about. So if we have this, if this is our chirality center, for instance, and then we have this 4 substituents. Now you can see there is this ash wedge, and you can see this one here, which is a thick wedge. We call this the ash wedge, and we call this the thick wedge. Now, the thick wedge you are seeing here means that it is moving away. We have the thick wedge and the ash wedge. So as I said, the thick wedge means that it is moving towards you. That means it is coming towards you. While the ash wedge means that the atom is moving away from us. So these 2 lines that are not having any, that are just plain line, means the image are on the plane. They are on the plane. They are just the way they are, like they're on paper. But this one, the thick wedge, is telling us that the image is moving towards us. While the ash wedge is telling us that the image is moving away from us. The same thing is what occurs here. Now, I said earlier that the smallest priority, which is this number 4, is supposed to be moving away from you. The smallest priority is supposed to be pointing away from us. So it means that the smallest priority is supposed to be on this arch wedge. Is that okay? Not on the plane and not on the thick wedge. So whenever it is not on the arch wedge, what we do is we reorient that atom. Meaning that after I finished giving priority and I'm moving from 1 to 2 to 3, is that okay, to 4, which is the way I'm supposed to move, I must turn the orientation to the other side. So if the orientation is moving to the right, as long as the lowest priority is not on the correct place, which is supposed to be pointing away, then I turn the orientation backwards. That's the easiest way to understand it. You don't, there are so many ways people can explain that, but the easiest way to understand it is that you should just look at it whenever the lowest priority is not on the hash wedge. That means the lowest priority is not moving away from, it's not pointing away from you. Then whatsoever orientation you get, you take it to the other side. Another important thing I need to mention to you is that in that case, you can see here, we have given priority, assuming we don't know what are in all this place. We are just, it's just a blank structure. Let's assume whatsoever here is the first priority, whatsoever here is the second, whatsoever here is the third, whatsoever here is the fourth. Now, if I need to move, move from the first to the second to the third, so that I can know what configuration it will be having, you will move. This is number 1. You can see I'm supposed to move from 1 to 2 to 3. Is that not so? But in the case of this one now, my 4 is, my 3 is in between. I can't move directly from 1 to 2 to 3 to 4. So what I do is I move, you take your pen and you turn 1 to 2. You can see I've moved from 1 to 2 to 3 to 4. Is that not so? Now, if you look at the way this turning is, assume it is a vehicle that you are riding and the vehicle is going like this. Where are you turning to? To the right. You can see if I'm turning my hand like this in a vehicle, I want to turn to the right. Is that not so? So it means this is turning to the right. That is supposed to be your rectus, which is right. But because my lowest priority is not on the hash wedge, is not pointing away, automatically what I do is that I reverse that order. I reverse the order. The reason I'm reversing the order is because this 4 is not where it's supposed to be. So if I reverse the order, this is what, as though I am turning to the left, and I call that S. So the configuration for this one would be S. I know you might not get it too well that way. Let's try doing this one. You can see our lowest priority again. It is not on the hash wedge, which is supposed to be pointing away. So it means that when we move from 1 to 2, and we move from 1 to 2 like this, you can see it is moving in one direction. If I'm riding a vehicle and I'm turning like this, where am I going to? To the left. So that means that's S, sinister. Now, but because the smallest priority is not where it's supposed to be, I reverse it, and then the correct answer will be R. Now, you wouldn't find this kind of explanations in textbooks. Even if you read it, you wouldn't see explanations of this type, but this was a way that I was able to simplify it for myself, and I've understand it that way. And I will encourage you to pay close attention and get it the way I've explained it. We'll see some other examples along the line. It will also help you to sharpen your understanding of that concept I just explained. So let's see this. Now, assigning configuration to a chirality center. So now this is our chirality center now, for instance. Just like the explanation I've already given, you can see our chirality center here, which is this, as priority 1, 2, 3, 4. But what do you observe here again is that the fourth one is not on the arch wedge. You can see in this case, they use dotted lines. If you use dotted lines or the previous diagram you saw, it's still the same thing. It is not on the arch wedge, so it means that it is not, the smallest one is not in the correct place. So what do? Is that we do it normally. This is 1 to 2 to 3 to 4. So you turn like this, 1 to 2 to 3 to 4. If I'm driving a vehicle and I'm going like this, where am I turning to? I'm turning to the left. That's S. Is that okay? But because my number 4 is not in the correct place, I reverse it. So if I reverse it, S become R. So the configuration of this is going to be R configuration. Now this is the mirror image of this. Of course, every mirror image of any molecule, we have the opposite configuration. If the configuration is not opposite, it means they are not mirror images. That's one of the ways we can confirm if two molecules are actually enantiomers. Enantiomers mean that they are non-superimposable mirror images of each other. So if I give you two molecules and I tell you, are they enantiomers or not? What I'm asking is that, are they mirror images? One of the easiest ways to know is to check the configuration. They must be opposite. If this is R, this must be S. Now let's see if this is S. This is priority 1, which is on the wrong place again. Priority 1 is on this arch wedge, which it must be, because you can see it's a mirror image. The part that is ending here is the part that must start here. They are mirror images of each other. So again, I will move from 1 to 2 to 3 to 4. If you see the way I'm moving, this is like driving to the right. Is that also? So it's supposed to be R, but because my smallest priority is not in the correct position, I reverse it, and that gives me a S configuration. I believe this is very clear and straightforward. I believe it is very clear and straightforward. So let's move on and see worked example. Now let's rank the following sets of substituents. Now let's assume there's a chiral center, a carbon, carrying these 4 different substituents, and I want to rank them. Which one will be first, which one will be second, which one will be third, which one will be fourth. Because if you don't rank correctly, there's no way you can be able to get the correct configuration. So let's see, let's rank it together. So this is hydrogen. Anytime you say hydrogen, it always has the lowest ranking, because of course hydrogen has atomic number of what? 1. So let's put the atomic number first. For atomic number is atomic number 1. This is oxygen with atomic number what? 8. This is carbon with atomic number 6. This is carbon with atomic number 6. So automatically, I already know which one will have my lowest priority, because this one is having 1. So priority for this is priority 4, the lowest ranked. Priority for this will be the highest, because this is 8 and these 2 are 6. So this one will be priority 1. Automatically carries priority 1. I believe those two are clear. Now, what we are looking for is priority 2 and 3. But the two of them have the same atomic number. So what did the second rule say we should do? You move on to the next atom. So what's the next atom? Another carbon, which is 6. What's the next atom? Another carbon, which is 6. What's the next atom here is the hydrogen, because there are no more carbons. So the next hydrogen is what? 1. This one here, the next atom is not hydrogen, because indeed there's hydrogen here, but if I draw this structure out, these 2 hydrogen will be facing up and down, and this carbon will also be directly attached to this oxygen. I believe you know what I'm talking about. If I want to draw out that structure, this is how it will be. This will be carbon carrying a hydrogen up, carrying a hydrogen up, down, which is our H2 that you can see here, and then it will be directly attached to it will be directly attached to OH. So this, what I do here is this ending part here. So what I'm trying to show you there is that that carbon is also directly attached to this oxygen. So we'll use the oxygen instead, and the oxygen is what? 8. So since this oxygen is 8, it means 8 is higher than 1. Is that not so? So this one will be having a higher priority, which will be our priority 2. And then this one, of course, becomes priority 3. So that is how to rank them. This is one of the most important things you need to know how to do. This is priority 1, priority 2, priority 3, priority 4. After doing that, then you need to find out, is priority 4 on the arch wedge, that is on the part of the structure pointing away. If it is not, don't bother yourself. Don't move it. Most textbooks, most texts that you and you'll be able to reach, you see, they'll tell you to change it, change the position, and then start doing the configuration. That will give you a lot of problems. So don't bother yourself. Just move from 1 to 2 to 3. In case it's not possible to move, if there's a 3, if there's a place where 3 is in between 1 and 2, move from 1 past the 3 to the 2 to the 4. Always pass the 3 instead of the 4. Is that okay? We shall see when we begin to solve some questions. We shall see how that applies. So let's move on to this second example. So in this second example now, we have S, which is sulfur. We have S, which is sulfur. Sulfur has atomic number of 16. We have carbon at atomic number of 6. We have carbon as atomic number of 6. We have sulfur as atomic number of 16. So automatically we know these two, we already are the two contending for the first ranking, because these two are already below them. Okay, so we move on to the next one to settle the scores between these two. So how do we settle the score? We move to the next one. The next one is hydrogen, which is 1. The next one here is still sulfur, which is what? 16. So automatically this one wins the race and gets priority 1. This one lost the race, but we still have priority 2 because both of them were the one competing. So then we'll come back to this. Now these two are also competing for the remaining priority 3 and 4. So we move on to the next one. The next one is not hydrogen. Don't make that mistake because this formula is written in the condensed form. This hydrogen are up, hydrogen down. This carbon is also directly attached to S, which is sulfur. So you have to move on to S instead of hydrogen. So sulfur has atomic number of 16 again. This one is directly attached to hydrogen because there's nothing else. Okay, so 1. So therefore, this one automatically gets priority 3. And this gets priority 4. So you can see sometimes priority 4 is not hydrogen. It can also be other molecules depending on the substituent around that particular atom. So that is how to solve that. Very simple and straightforward. So our configuration at chirality center. Okay, lowest priority group is pointed away and directed, and direction of higher 3 is clockwise or right turn. So when it is our configuration, as we've said, you must make sure the lowest one is pointing away. And then by the time you turn from 1 to 2 to 3 to 4, it must be going in the clockwise direction before we can say it is a R configuration. So this is a sample of what it looks like. You can see moving to the right as though you are driving, turning a steering. Always use a steering to recollect whether the arrow is moving right or left. It always helps. So, example of applying sequence rules. If lowest priority is back, that is clockwise is R and counterclockwise is S. So once you have established the fact that the lowest priority is pointing away, then once it is turning clockwise, it is R. Once it's counterclockwise, is S. But as I told you, once it's not turning away, you don't need to change it, the position. All you need to do is move your arrow from 1 to 2 to 3, or if 3 is in between 2, still move it across the 3 up to 4, and then reverse that direction. Reverse whatsoever you get. And then the reverse will be the answer. So I said it before, R is rectus and S is sinister. Okay, you see the case in glyceraldehyde. In glyceraldehyde, first thing you need to do is to identify the chirality center before you can begin to tell whether it is R or S configured. I've taught you how to identify chirality centers. If you don't remember how to identify chirality center, there's no way you can even solve any of these questions. There's no way you can give priorities because it is the chirality center that will determine where the priority lies. So let's look for chiral center in this structure. In this structure now, if you look at the carbons, if you consider this carbon, you can see it has 2 hydrogen. It can be a chiral center. If you see this carbon, it is bonded, double bonded. Once you see a double bond, it can be a chiral center. Of course, this is the only carbon left. When you see a junction, every junction is a carbon, okay? Like I said before, if I do something like this, each of these edges represents carbons, and anything that is not shown represents hydrogen. So it means this edge here is a carbon. This carbon is attached to this 1, 2, attached to this 3, attached to this 4. All the substituents are different. You can see this CH2OH, this CHO. So it means all the substituents here are different. So since they are all different, it means this carbon at the center here is a chiral carbon. So that's the first thing to determine. Once you determine the chiral carbon, then you begin to look at the substituents around it to determine the priority and what direction they'll be following. So let's give priority to them. This is hydrogen. Of course, once we say hydrogen, we know it has the lowest priority because it has atomic number of 1. We have oxygen here. This is atomic number of 8. This is carbon. This is carbon. So this is 6, 6. Okay. So this automatically takes our first priority because it's atomic number of what? 8. But these two are dragging, which we have the second priority. So how do I move? I move to the next one. What's the next one for this one? I told you, don't be deceived by when I write hydrogen in front, this hydrogen is actually on top of it. This carbon is also directly attached to oxygen. So because of it, I say carbon attached to double oxygen, 2 oxygens, okay? Now, this second carbon is also attached to oxygen, but it's attached to only 1 oxygen. So this one has the higher priority. That is where what we talked about during the rules. That's where it comes in. This one is attached to 2 oxygens. This one is attached to 1. So therefore, this one has the higher priority. So this takes priority 2, and this takes priority 3. Okay, all those have already been labeled there. So from that now, we already have our priorities made. After giving the priority, you now look at the smallest priority. Is it on the arch wedge? No. Our carbon, our hydrogen is not on the arch wedge. That means it is not pointing away. So what we just do is when we move our priority, we return it back. Is that okay? We return it back in order to show that it is not in the correct, that our lowest priority is not in correct direction. So, like we said, we then move it from the lowest priority, moves 1 to 2. If you look at this like you are riding a car, you will see it is moving to the right direction. But because our lowest priority is in the wrong place, we turn it back, and then it is going to be a S plus idea. The same thing occurs here. It will reverse and become a R plus idea. You can check that out yourself and understand it properly. Molecules with multiple stereocenters. Now, there are some molecules that have more than 1 stereocenters. I said stereocenters is the same thing as your chirality center. So some molecules have more than 1 chirality center. So in those cases, we are going to give each of the chirality center its own configuration. So let's see, molecules with 1 stereocenters can be R or S. 2 possible stereoisomers. So when a molecule has 1 stereoisomer, it can only be R or S. It cannot be both. But when a molecule has N stereocenters, it can have all the possible combination of R and S for each stereocenter. It means in this case, it can have different, it can have several stereocenters. Is that okay? R and S. So we are going to have 2 raised power n possible stereoisomers. The meaning of that is if I give you a compound and I ask you how many stereoisomers can that compound have? This n here signifies the number of chiral centers, which is also the same thing as your n number of stereocenters. Is that okay? Stereocenter is another name for chiral center. So if it has 5 chiral center, it means it will have 2 raised to the power of 5 possible stereoisomers. And then you do the math, 2 times 2 times 2 times 2 in 5 places, depending on how many stereocenters it has. So we also have what we call diastereomers. Diastereomers, we have molecules with more than 1 chirality center. They have mirror images, that is stereoisomers, that are enantiomers. But in addition, they can also have stereoisomeric forms that are not mirror images called diastereomers. So the compounds that we talked about that can have more than 1 chirality center, after they will have some images that are identical, that are mirror images, non-superimposable mirror images of each other, which are enantiomers. But they will also have some other stereoisomers that are not mirror images. Those ones we call them diastereomers. So let's see. Let's look at this that we have now. Okay, let me take this off. Okay, so if we look at what we have here, we have, let me take off this once. So here now, we have more than 1 chiral centers. How do I know? Look at this carbon here. This one is not a chiral center because it is bonded to double bond. This has a double bond. This is a carboxylic functional group. Another way to write this is C double bond O single bond OH. So once it has a double bond, we know it can be a chiral center. So this is not the chiral center. Let's move to the next carbon. This carbon is bonded to 1 carboxylic group, hydrogen, NH2, and then bonded to all this. So it means this one is bonded to 4 different substituents. And then we say, yes, this is a chiral center. The same thing with this, is bonded with hydrogen, bonded with OH, bonded with CH3, and bonded with all this on top of it. You can see it's bonded with all this. So this one is also a chiral center. So we have 2 chiral centers in this structure. Now, since we have 2 chiral centers, it means both of those chiral, each of those chiral centers, we have a name. We are going to name each one differently. So, but how many possible stereoisomers can I have? Since there are 2 chiral centers, it means I can have 2 raised to the power of what? N. And N is 2 because there are 2 chiral centers. So 2 raised to the power of 2 is equals to what? 4. So that is why I have 4 different stereoisomers. There are going to be 4 different stereoisomers. Now, of the 4 different stereoisomers, 2 are going to be mirror. These 2 are mirror images, so they are enantiomers. These 2 are also mirror images, they are enantiomers. But this and this are not mirror images, but they are still stereoisomers of each other, but they are not mirror images. So we say they are diastereomers. These 2 are not mirror images, we say they are diastereomers. These are not mirror images, they are diastereomers. These are not mirror images, they are diastereomers. So whenever we have more than 1 chiral centers, we are going to have enantiomers and we are also going to have diastereomers. So I hope you understand how I got the enantiomers. I said these ones are mirror images. Let's see how this goes now. So let's first name them. So the first thing to do after identifying your chirality center, the next thing to do is to what? Is to give priority. Now, this is a carbon, is that not so? So atomic number is 6. This is nitrogen, atomic number is 7. This is carbon, atomic number is 6. This is hydrogen, atomic number is 1. So it's going to have the lowest, that's number 4, that's 4. It's going to have the lowest priority, okay? The one here, which is nitrogen, is number 7, has 7. Atomic number is 7, it's higher than carbon. So therefore, it is going to be having the highest priority, which is priority 1. Now we have 2 carbons, carbon up here and carbon down here. Both of them are going to be fighting for priority 2 and 3. So let's see which one has it. This other carbon here is directly attached to another carbon. I say this carbon here is directly attached to another carbon. But don't forget, even though it is directly attached to another carbon, it is also directly attached to a oxygen. Okay? It's directly attached to a oxygen. So because it's directly attached to oxygen, that's the one we'll consider. Because oxygen is greater than carbon, so we'll come to oxygen. I said oxygen is what? Atomic number 8. What of this one? The next thing is attached is also oxygen, so 8. They are still dragging 8, 8. So we move to the next thing. The next thing is attached to, we don't need to move to hydrogen because there's a carbon down here. So we'll move to the next thing. It's attached to a carbon. This is a carbon. Is that okay? Which is 6. But this one is also attached to another oxygen. Is that okay? So because it's attached to another oxygen, it means that now oxygen is greater than carbon. So this one takes priority 2. I hope it is clear. And then this one takes priority what? 3. Now we have to move from 1 to 2. Now another thing you need to know is that in this case, you can see there is no arch wedge. The reason is that this structure we are using here is a different type of structure. In this one now, this middle line is the line that is moving away, is the one pointing away. This middle line is the line pointing away. This one you can see they are thick lines, they are the one pointing towards you. So the smallest priority is supposed to be on the line pointing away, which is the middle line. And you can see the smallest priority hydrogen is not on the middle line. So it means that whatsoever direction we get, we must reverse it. So let's move from priority 1 to priority 2. Even though this is not priority 3, we must still move from 1 to 2, okay? So priority 1 to priority 2, you can still curve down a bit, and then let's put our arrow. How is this moving? If I was driving a car and I'm turning my hand in this direction, what am I trying to do? I'm trying to turn to the left. Is that also? So it means this is the left direction. But because our hydrogen is not on this straight line, which is the one pointing away, then we have to reverse this backward, which means this point is going to be what? R. Is that okay? This point is going to be R. And what carbon is this? Yeah. What carbon is this? This is carbon number what? This is carbon number 1. Not priority now. I'm talking about position. When we are counting carbon, this is carbon 1, carbon 2, carbon 3, carbon 4. So this is carbon number 2. Because it is carbon number 2 and the configuration is R, we write 2R. Do you see that now? So we have already named this one. We have to move on to the next one. We have finished naming the first one. We move on to the next one. Now let's move on to the next one now. The next one is going to be this second carbon. The smallest parity again is still hydrogen. The one with the highest parity here, this is a carbon, this is a carbon, but this one here is a oxygen, so it is 8. It is a higher parity, so it is going to get parity 1. So the two competition is between this and this. Between this and this now, both of them are 6, so we need to move to the next atom they are attached to. This one is attached to a nitrogen. Is that okay? It's attached to a nitrogen, is attached to a carbon, but a nitrogen is higher, so we'll take nitrogen. Nitrogen is 7, whereas this one is attached to a carbon, which is 6. So automatically, this takes the parity. And the parity comes here and becomes parity number 2. And this one, of course, takes parity number 3. Very simple. We also move again from 1 to 2. You can see this one is moving in, excuse me. You can see this one is moving in a left as though I'm turning to the left. But because hydrogen again is not on the center, we turn it to the other way around again. So it will also be a right, it's also moving right, which is also S. So it means this is also going to be a what? A S turn. So, sorry, a R turn. This is a S, the original direction, but because H is not on, the lowest parity is not on the arch wedge, we turn it back, meaning that this is going to be what? R. Now, we are putting 3R here because this carbon here is carbon number 3. This carbon here is this carbon number 1, carbon number 2, carbon number 3. So this is 2R, 3R. When we want to name this compound, whatsoever name this compound as, we are going to call it 2R, 3R, the compound. So if the compound, for example, is a tartaric acid, I'll say this is a 2R, 3R tartaric acid. So that is how to call it. Is that okay? So that is the name. So for the mirror image, which is this, of course, we can easily see this, the mirror image. Whatsoever is on this side, if you put a mirror in front of something, it is that direction that you see first. And then this one here, of course, you see it moving away. Every other thing is there. So it means if this is actually a mirror image, it must have the exact opposite. If this is 2R, 3R, this must be 2S, 3S. We can check it out to see that we are correct. Of course, we've established that these two are the chiral centers because they are attached to 4 different groups. And then if I pick this is the lowest parity, like we've seen already in the previous one. We said this is the highest parity, parity 1. We also established that this is going to have parity 2 from what we've done here already. I don't want to go over that again. And this is going to have parity 3. So moving from 1 to 2 again, 1 to 2 is this direction. What direction am I turning if I'm riding a car in this direction? I'm turning to the right. But H is not on the straight line, which is the line pointing away. So we are going to take it backward, which is S. So that's why we have 2S. Can try your hand on this. You also see it is going to be moving towards this direction. That's why we have 3S. So pause the video and try out to do this one on your own. Okay, let's do it together now. So if you did it correctly, you are going to get a 2R and 3S. So let's see how we came about that. Of course, again, these are chiral centers. It's the same molecules. These are just different isomers of it. They are just different isomers of the same compound. So this one now, in the case of this one, you can see our NH2 and OH are in different directions. So it's an isomer of this. They are the same compound, just the way they are oriented. Now, from here now, this will take my parity 1, of course, as I've established before. This is my parity 4. This is my parity 2. This is my parity 3. Now, I'm going to be moving from 1 to 2 again. 1 to 2. Now, as I'm moving from 1 to 2, my hydrogen is not on this straight line, so it has to reverse. This reverse now, if I'm moving in this direction, it means I'm riding to the right. So that gives me carbon 2 as a configuration of S, and that's 2S, okay? So for the second one now, parity, this parity 1, this parity 4, this parity 2. We've already said this before from this place, so I'm just going over the same thing, and this parity 4. So moving from 1 to 2, which is this way, our hydrogen, which is the lowest parity, it doesn't have to be hydrogen, but in this case it's hydrogen, lowest priority is not on the central line, so we reverse. Most cases where we have compounds having more than one chirality centers, the lower priority are usually not on this center, so you always have to reverse your answer. So if you reverse this, this is turning. If I'm riding and I'm going like this, I'm turning to the left. So this is 2R3S. You see, this is the mirror image because when this is 2R, this is 2S. When this is 3S, this is 3S. So the mirror image must have exactly the opposite configuration. That's how you can establish whether two molecules are actually enantiomers, that is, mirror images of each other. So how many enantiomers do we have here? How many enantiomers? If I give you a compound and I ask you to tell me how many stereoisomers can we have in that compound, what you will do to find out how many stereoisomers we have is simply to what? You just say 2 raised to the power of n, where n is the number of chiral centers. 2 raised to the power of n, where n is the number of chiral centers. This will tell you how many stereoisomers, not how many enantiomers we have. We are going to have 2 raised to the power n stereoisomers. In this case, n is 2, so this is going to give us 4 stereoisomers. But how many enantiomers are we going to have? So how do we arrive at that? To know the number of enantiomers, you are not going to see this in the slide, but I'm going to ask you. That's why it's important for you to listen to all these lectures. The formula for that is 2 raised to the power of n minus 1. To know the number of enantiomers, number of mirror images. So 2 raised to the power of n minus 1 is 2 raised to the power 2. In this case, n is 2, so 2 minus 1 is 1, which is equals to 2. So the number of enantiomers is 2. You can see is 2 pairs. This one here is an enantiomer. These 2 forms one enantiomer because they are mirror images. So this is a pair, which is one enantiomer. This is another pair, which is another enantiomer, making 2 enantiomers. But for diastereomers, in the case of diastereomers, we are going to have, let's see, these 2 are going to be diastereomers because they are not mirror. Once they are not mirror images, it means they are diastereomers. That's just what diastereomer means. Just pair things that are not mirror images of each other. So these are not mirror images, so they are diastereomers. These are not mirror images, so they are diastereomers. These are not mirror images, so they are diastereomers. These are also not mirror images, so they are diastereomers. So how many diastereomers do I have? 4. So to get your diastereomers are often the same number as your number of stereo centers. The number of stereoisomers, which is what we calculated here. So that is how to go about that. I believe it is very, very clear. So enantiomers, I've already said that. Just a recap. I said they are stereoisomers that are non-superimposable mirror images. Diastereomers are also stereoisomers, but they are not mirror images. And of course, another example is tartaric, which we have seen before. Now, that brings us to meso compounds. Now, we have some compounds that we call the meso compounds. Tartaric acid has 2 chirality centers. Tartaric acid was what we saw in our previous slide in the last class, and that's what we are reviewing again. Tartaric acid has 2 chirality centers and 2 diastereomeric forms. Is that okay? There are 2 diastereomeric forms and there are also 2 chirality centers. One form is chiral and the other is achiral, but both have 2 chirality centers. We'll see what that means soon. An achiral compound with chirality center is called a meso compound. Now, it means it is possible for a compound to be achiral. Achiral means that compound is not a chiral compound, but yet that compound has center of chirality. Normally, any compound that has a center of chirality, that is a chiral center or stereogenic center, like we've talked about, a carbon carrying 4 different substituents, if it's present in any compound, that compound is supposed to be what? Chiral. But there are some compounds that have chirality centers and yet they are still a chiral compound. Why? It is because they have a plane of symmetry. Very important statement. If I ask you to tell me, define meso compounds. Meso compounds are the compounds compounds having chiral centers but are achiral compound because of the presence of a plane of symmetry. They have what we call a plane of symmetry. And this is the reason why, though they are chiral, though they have chiral centers, they are not chiral compounds. The two structures on the right in the figure are identical. So the compound 2R and 3S is achiral. The meaning of this is, if you look at this compound, what a plane of symmetry means is that there is a way it is possible to draw a line such that the upper part and the lower part are exactly the same. That means they are identical. The implication of that is that if I draw a line and the upper part and the lower part becomes mirror images of each other, it means even though there is a chiral center, it will cancel each other out. The chiral centers will cancel each other out, hence making the whole compound to be what? Achiral. That means not chiral. So once a compound has a plane of symmetry, we call it a mesocompound, meaning that though it has chirality centers, it has a plane of symmetry. That means there is a way I can rule a straight line here such that this upper part is a mirror image of the lower side, such that they will cancel each other out. Their chirality will cancel each other out. So that is, of course, tartaric acid is what I also explained here to show you that it has two stereogenic centers and 2 raised power 2, that's 4 possible stereoisomers. So why not enantiomers? Why not enantiomers? So sorry for that break. Now look here, we said these are same compounds, even though they look like they are different compounds. For enantiomers, the same molecular formula, same connectivity, they are mirror images, and they are non-superimposable. Once it is superimposable, it means it is what? It is chiral. In the case of this molecule, they have a plane of symmetry. So there is a way to turn these molecules such that both of them are superimposable. We can't see that on plain paper, but if you look at the model of these molecules, we observe that they are actually the same. So because of their plane of symmetry, which is what I've explained, this is why they are not enantiomers. Even though they look like they are mirror images of each other, they have a plane of symmetry such that they can cancel each other out. A compound with at least two stereo centers that is achiral due to the presence of a plane of symmetry is called a mesocompound. So, okay, let's finish up with this. Molecules with more than 2 chirality centers. So sometimes you can have molecules with 3, 4, 5, 6 chirality centers. The same way we name the two is the same way we name them. You just continue naming each one. Now, molecules can have very many chirality centers. Each point has 2 possible permanent arrangements, R or S, generating 2 possible stereoisomers. So the number of possible stereoisomers in the chirality center is 2 raised to the power of 10. I think we've said that clearly. Cholesterol has 8 chirality centers. So you need to also know that there are some molecules that have many chirality centers. For example, cholesterol has 8 chirality centers. But I won't give you compounds having more than 2 chirality centers for you to tell me the configuration. But I can give you compound with so many chirality centers for you to tell me how many chirality centers are there. You don't need. I won't ask you to give me the R or S configuration, but I can ask you to tell me how many. I can draw a cholesterol and tell you how many chiral centers are there. So you need to just count it and know the number of chiral centers. In cholesterol, there are 8. Physical properties of stereoisomers. Enantiomeric molecules differ in the direction in which they rotate plane polarized light, but their other common physical properties are the same. So when compounds are enantiomers, they have exactly the same property. The only difference between them is the way they rotate a plane polarized light. If it is the R configuration, it rotates plane polarized light to the right. If it is the S configuration, it rotates a plane polarized light to the left. If you don't understand what I'm talking about now, go back to the last video and watch where we talked about the polarized light, and we talked about how light rotation occurs when they hit a chiral center. It has been explained vividly in last class. But for diastereomers, they have complete set of different physical properties. So we can see some set of physical properties stated here. You don't need to memorize. These ones are the properties of tartaric acid. Now, we also have what we call a racemic mixture. A racemic mixture. I've talked about meso compounds. Now we are talking about a racemic mixture. Racemic mixture and their resolution. A racemic mixture is a 50-50% mixture of two chiral compounds that are mirror images, and it does not rotate light. It is called a racemic mixture. Now, they don't rotate light because they contain 50-50% of two chiral compounds that are mirror images. So it means when one is rotating the light to the right, the other one is rotating the light to the left, and then they cancel each other out. So at the end of the day, it does not rotate the light at all because they've canceled each other out. 50-50% of two enantiomers. Two enantiomers together, 50-50%, then we call that a racemic mixture. The pure compound needs to be separated at resolved from the mixture, called a racemate. So the mixture is called a racemate, and we need to separate the pure compound. And that's what we do in the laboratory. We are doing an experiment on this now. We could look at a 50-50% mixture of two compounds and try to separate one of them, because it's not really useful when they are together in racemic mixture. We need to separate them. So to separate components of racemate reversibly, we make a derivative of each with a chiral substance that is free with enantiomer, resolving agent. So we call that a resolving agent. We take a derivative to separate component of racemate, that is the racemic mixture. We make a derivative of each with a chiral substance that is free of its enantiomer. So we call that kind of a the derivative we are introducing, we call it a resolving agent. This gives the stereomers that are separated by their differing solubility, and the resolving agent is then removed. So that's how we separate the racemic mixture. It's important for you to know this because you can be tested on these facts. So chirality in nature. In nature, we also have chirality. Stereoisomers are readily distinguished by chiral receptors in nature. Properties of drug depends on stereochemistry. Most drug, 90% of drugs, depends on stereochemistry, because you need to start looking at, are they the R or the S configuration of that drug? Because like I said when we begin this course, is that when you take a drug that is supposed to have the R configuration, has the S configuration, it won't do the same work because they are not the same. So we take note of all this stereochemistry in drug production. Think of biological recognition as equivalent to 3-point interactions. Many biological recognitions involve the use of stereochemistry. So on this note, we have come to the end of stereochemistry. Next class, which I will also be releasing the video later this week, we are going to be looking at another topic entirely as we continue our journey in CHM 322. So thank you so much for listening, and please try to go over this video at least twice or thrice and ensure you jot down things that you are learning so that you can always refer to it. So thank you so much. We'll see you next time.